Good evening and welcome to this class of stochastic processes. So today we'll see and today we'll see what a stochastic process is. So a stochastic process X is a collection of random variables which are indexed by uh, an index set T. So this is a collection of random variables. So what we have here is so T belongs to capital T, which is known as the index set. So this index set is usually interpreted as type because we have many random processes. We see at what time what happens in the some module, some system of a module. So it is indexed by the time, but it need not be time always. You could have it as space or some other physical interpretation of it. So hence index set, but generally we'll be using time as an index. Okay, and the randomness here is in xt. So xt is a random variable. And this is known as state of the stochastic process. So yeah, these are the things that you need to define for define a stochastic process. So first you need an index set over which you index it, and at each element of that index you have mm, a random variable. So so you give me a member of the index set, then I'll give you a random variable which defines in what state the stochastic process is. The index set is often interpreted as time. So you give me a time and I'll give you what the random variable is for a sample path. But it need not be time always. So what you have is you have the index set T. T can be countable. If T is countable, then we call it as discrete time stochastic process. If T is a continuum, which is just continuous, it's not countable. We call it continuous time stochastic process. We'll see both these types of process in this course. So DTMC is one of the example for discrete time stochastic process. Poisson process and CTMCs are examples of continuous time stochastic process. So we'll see both of them. Okay, so how do you characterize a stochastic process? You characterize it by its distribution, finite index distribution function. So that is given by, so we have a distribution function of fx, which maps from Rs to 0, 1 for all finite subsets S, which is a subset of an index set. So you have the whole index set. You take a finite subset of the index set and you write the distributions of the random variables at those finite points of the uh, index set. So what this means is fxs. So this takes so this is a function from Rs to 0, 1. So it takes a vector which has S elements. So it's R, it takes a vector in RS. So you have x1, x2, and so on to xs. So this is defined as probability of the event intersection. S belongs to the finite subset that which is been chosen, and xs. So this is the um, here instead of indexing it as an argument, what I'm indexing it as x. So yeah, this is the night slide notation change I have done here. So I will indexing it at xt. So S is the index, omega is the random event that occurs. And yeah, this is less than or equal to xs. So this is what the finite distribution of a stochastic process. So to mathematically define a stochastic process, you take finite number of indices and define what the distributions are at those points of instances. Okay, so some basic quantities of what stochastic process. So you have mxt, which is the expectation at a given index t, where t belongs to us. And you have the covariance, the correlation, autocorrelation, and the covariance terms, which are given by these terms. So these are some of the uh, metrics which you can calculate given a stochastic process. So what we'll do is I'll give you two examples where we can calculate these three metrics. So the first one is you have a 100 rupee note in an account. With interest rate R. So which is compounded annually. So you want to find the three terms of the stochastic process. I will tell the stochastic process where the stochastic, where the randomness is. So calculate these three terms. Okay. So the randomness, what you have random is xn is the value of the amount in the account at year n. And how does xn vary from year to year? Is xn is given at 100 into 1 plus r power m, where r is the interest rate. R is the interest rate. But what you have here is r is distributed uniformly over 0.04 and 0.0. So the randomness is at what is the interest rate you get at each and every. That is your randomness. And based on this randomness, you get a sequence of random variables. So you get a random stochastic process where you have where you don't know the value of amount that will be in your account after some 10 years. So first you want to find expectation of xn. So this is basically expectation of 100 into 1 plus r whole power n, which is 100 into expectation of 1 plus R power. Now, since R is uh, distributed uniformly, 0.04 and 0.05. So again, creating new random variable, which is 1 plus R. This is distributed uniformly in 1.04 and 1.0. So I can replace here with 100 into expectation R prime whole power. And then you can, since it's uniform, you know the density function. So it was from 1.04 to 1.05. And it's 100 into. So if you calculate this, you'll get 10 power 4 n plus 1 into 1.05 whole power n plus 1 minus 1.04 into the power n plus 1. So here what you see is the expected amount, uh, expected value of amount in the account that you get at n here is a function of f. This is a function of n. So it depends on what year you want. So each year the expected uh, amount in the account keeps on increasing. That is what this uh, this thing informs you. We'll keep that in mind because we want to define something as stationarity and independent increments. So for this stochastic process, we see that the uh, expected value of the random process as time increases uh, is a function of n. Next, we calculate the autocorrelation function for n comma k, which is basically expectation of xn and xk. This is expectation of n into 1 plus r whole power n plus k. So we still have 10 power 4 expectation r prime n plus k, where r prime have defined above. And this will get basically as 10 power 6 by 10 power 8 by n plus k plus 1 into 1.05 n plus k plus 1 minus 1.04 n plus k minus 1. So here also you see the autocorrelation function is also a function of n and both k, but it's not a function of uh, the difference between n k. So we'll keep that in mind. So this is just a function of n and k, but not a function of n minus k. Covariance sum can calculate. We'll be just looking at these two terms. Okay, this one, the example given here, as you can see, it is a discrete time random process. Because the index set here is each and every year. So year is actually you are counting it using the natural number. So your first is second year, third year, fourth year. So the natural numbers are a set which is countable. So the index set is countable, and hence it's a discrete time random process. Similarly, you can actually, so here, even though the randomness that comes through is due to a continuous random variable. So this is a continuous random variable. Does not imply that the uh, stochastic process would be continuous. Here the stochastic process is discrete, even though the randomness that comes from the the randomness that comes in the stochastic process comes from a continuous random variable. I hope that point is also clear. Okay. Mm. So second example. So now we'll do a simple example for continuous time stochastic process. So xt is equal to a plus bt. This is your uh, continuous time random process where a and b are distributed with normal distribution, mean 1 and variance 1, and a and b are independent. So now you have you need to find mxt, which is expectation of xt, which you can write as expectation of a plus bt. So from the linearity property of expectation, we can split this expectation as expectation of a plus uh, expectation of bt. The expectation of a is just 1 because from the normal distribution plus t, there is nothing random in t. So t is a deterministic term. So t comes out and expectation of b is just expectation of b. This is for all t belongs to 0, comma. So this is defined for all t belongs to 0, comma. Yeah, we have the mean. And here also you can see that the mean is a function of time. So it's a linear function. T, the uh, mean of the stochastic process at each time where the index settles continuous. So similarly, we'll calculate the order correlation between T1 and T2. So you have expectation of xt1 into expectation of xt2. So you have expectation of a plus bt1 into a plus bt2. So this you have expectation of a square plus abt2 plus abt1 plus p square t1. Now again you apply linearity. And then motivator is 2 plus T2 plus T1 plus T1 T2 plus 2 into T2. This is for all T1 comma T2 belongs to 0. Here also you can see that this is a function of T1 and T2, not a function of T1 and T2. So yeah, next what we'll see is independent and identically distributed process. So next we'll see is independent and identically distributed process. So let X be a stochastic process. This stochastic process is IID if for any finite subset of the index and you have a vector which belongs to RS. FXS here you have the notation is x1, x2, and so on. XS. This is a joint distribution notation. So you have multiple. It's similar to it's a joint distribution notation. So here you have the random variables and the instantiations of random variables. Sorry about that. Yeah. Then you have x1 to xs and then some distributions. This we know as probability of intersection of xs less than or equal to xs. So if this fructifies out, then so we have used both the independence and identical property of the so this step is using the independence. You fructify the mm, probability distributions, and then since they're identical at each random instantiation of the stochastic process, you get the same distribution. So this is independent and identical. You use both of these, and so if this happens, then you say that a random process is uh, independent and identically distributed process. Okay, so one remark here is independent random process and two random process are independent are two different concepts. Okay, so next we have stationary process. So again, let X be a stochastic process. And this stochastic process is said to be stationary if the joint distribution for a finite subset of the index set S is shift invariant. So what does shift invariant mean? So if I have X 1 plus T, X 2 plus T, so X S plus T, if these both are equal, the distributions the shifted so are equal. So what this basically means is this name is shift invariant. Shift invariant. So basically, if you draw a map, so this is your index, the index at index, and the state space. So if you have um, a time instance 1, 2, 3, 4, 5, if you have the distributions of x1, x2, x3, x4, and x5. These distributions is same as having the distributions at 10, 11, 12, 13, 14, 15. So they might not be the same, but the distribution that you up see when you see here is the same the distribution that you see here. So once you shift the random process also you observe the same joint distribution, then the process is not stationary. So IID implies stationary. I'll not be doing the proof in this course, but if you want, you can ask me in the ask people to do the proof. So IID implies stationary, but stationary does not imply IID. So we'll give a quick example of this. Uh, One example is I generate a random process such that x0 equal to 0, x1 equal to x0, x2 equal to x1, and so on. You can see that once you know the distribution of x0, all the others would have the same distribution. So how many times you shift the take any number of joint distributions, uh, they'll they'll always be shifted variant. So this process is stationary, but it's not independent. It's identical because once you fix x0, each and every instance of the of the stochastic process would have the same distribution, but it's not independent because x1 depends on the value of x. The distribution of x1 depends on the distribution of x0. The distribution of x2 depends on the distribution of x1. They are not independent. So this is stationary, uh, but not independent. So next, I want to introduce a concept known as independent increment property. So for this, what we'll do is we'll consider a discrete time process, discrete time stochastic process. Such that so you have uh, stochastic collection of random variables, and I'll define how the is the sum of the previous plus step. So this is basically an example of a random walk, which we'll discuss later. But I'm just giving an example. So yeah, so U is again a random process which has ULs and belongs to one. These are IIDs. This collection of steps are IIDs. So what this basically, and you also have x0 equal to 0, the starting point. So basically, so you have, uh, so suppose at, yeah, so this is your time, 1, 2, 3, 4, 5. So if I say, okay, the One of the example is if I say UN is distributed. So UN, so UN can take two values. Suppose UN, probability of UN equal to 1 equal to probability of UN equal to -1 equal to 0.1. So basically, uh, if UN can take 1 and -1 as the two values and each with some probability. So one instantiation of this would be, so it rises up by 1 and then it again decreases by 1 and then it decreases by 1 and this is -1 and then again it rises. So it will be something similar to this. So a sample path would be of this one. So this is a random. This is a random walk. At each time instance, it either takes +1 or -1 as a step. This is a random walk. We'll show that random walk has independent increment property. So before that, what we'll do is first we'll find what xt is. So xt is equal to xt plus xt minus x0 because x0 is 0. So I can subtract it with x0. Then what I do is xt minus xs plus xs minus x0. So now I know xt minus x0 is this, and then I take xt minus xs. This is equal to xt minus x0 minus xs minus x0. So this is basically a summation of the step functions from s to t minus 1. Therefore, xt minus xs, this depends on us to ut minus 1, whereas xs minus x0, this depends on u0 to us minus 1. As u is an IID stochastic process, these both are independent. It shows the independent increment property of random. We'll come back to independent increment property later while we just go to Poisson process. So now we'll start Poisson process. But before that, we'll go through some motivation of why Poisson processes are studied. So Poisson process basically counting process. So so um, counting process. So what does mean is some event happens at random times. We want to know the frequency at which these random events happen. So basically, this random process keeps track of or counts how many times an event has occurred. So we'll start with the motivation will start with some small examples. So you have a road and some cars pass through it. So you are observer here. You want to know how many cars pass through here. You want a stochastic process model. Uh, it says, okay, I'll want to know how many car passes through. That is my stochastic process. So what you do first is you define a random variable. That random variable is number of cars passed in an hour. This you decide arbitrarily. You say that I want to um, see how many cars has arbitrary. What you do is you sit down and you take an assumption that okay, um, all hours are independent. Like if I watch 1 hour, the number of cars, they are IIDs. So basically they are IIDs. So any hour is no different than any hour, which obviously is not true while modeling real life systems, but we take an assumption that all hours are independent and identical. So it doesn't matter at what hour you're watching. If you're watching for an hour, uh, multiple number of times, or you have watched the same or multiple number of times, both will give you the same statistical results. Identical. So what you do is you sit down and you watch for each hour. You take a note of how many cars have passed. You take a note again. You take a note again. You take a note again. So what you get is the expected number of cars that pass through is maybe say 9 cars per hour. It need not be 9 because it's an expectation that you're calculating over all hours. So let's say it's some 6.3 cars per hour. So now this we term it as lambda. So lambda is the rate of number of cars that you see each and every hour. That you see each and every hour. Now you want a stochastic process which can model mm, this, which can model the number of cars that pass through a point. So the event is car passing through a point, and you want to model this. So the best approximation you can do is you can take that. Okay, first I'll give. So you have the binomial distribution. Binomial distribution. So if x is 1 with probability p, also this probability. So binomial distribution is it is so uh, x takes 1 to n. So it has parameters n and p, and probability that x equal to k equal to k choose n p power k 1 minus p power k minus n. So it is basically you have k successes and 1 minus p failures. So this is the binomial distribution that you put. See, and we know that expectation of a binomial distribution is n. Can model it in this way. Uh, NP. So now you say, okay, so what the binomial distribution says is you have a random variable. You conduct experiment multiple number of times. At each experiment, you see that whether success has occurred or failure has occurred. In all those events, mm, uh, so if you conduct it for n number of times, then what is the probability that um, k of those events I got a success and k minus n I got a failure. So you get a success with probability p and failure with probability 1 minus. So now what you do is lambda cars per hour, you say that, okay, I'll I'll I I'll split this hour into number of experiments. So I have 60 minute per hour and lambda by 60 cars per minute. So now because I'm modeling it using binomial distribution, so probability of x equal to k is equal to 60 ck, and I get a car at rate lambda by k for k time and 1 minus lambda by 60 k time. So this is an approximation. So what is the approximation? The approximation is, this is my 1 hour. So this is 0 to 60 minutes. I split this it into tiny intervals of minutes. 1 minute, 2 minute, 3 minute, 4 minute, and so on. At each interval, I observe if a car has passed on. So my end aim is I want to find the probability that total k cars have passed in 60 minutes. So the yeah, so this probability, what I've done is I have now split up here. So observe if a car has passed or not. The probability with which a car passes is lambda by 60. And the probability which it doesn't pass is 1 by lambda power 60. So at each time you get success or failure, success or failure. You get those and you see that what is the probability that k have passed through this. But since this is an approximation, one the point where you're approximating is, okay, so you have not displaced into 1 minute slots, but what if two cars pass in the 1 minute? So what you say is, okay, I can still decrease my granularity, and you say, okay, now I'll calculate the probability that x equal to k for second, 3600 seconds by k lambda, okay, so 3600 choose k, uh, lambda by 3600 whole power k into 1 minus lambda by 3600 whole power 3600 minus k. But even then the problem ends. So now you ask, what if two cars pass in 1 second? So what you need to do is you need to take the limit of this to limit of, so this as the number of slots that you have discretized into, and take it to infinity. Okay, so before that, I'll just give some. So limit x tends to infinity, 1 plus a by x whole power x equal to e power. So this is a standard result that we know. And if we substitute 1 by n equal to a by x, we get x is equal to na. Get limit n tends to infinity, 1 by 1 plus n, na equal to limit n tends to infinity, 1 plus 1 by n. Since the power a has nothing to do with this, is e power. The internal limit goes to units. This is also standard result that we know. Okay. So next, what we do is, so expectation of x. So what we want is the expectation of x. We we want to model the process under the assumptions that there is a constant rate at which the cars are going, but they are random. So at each every interval of time that you see, you want your expectation to be um, yeah, equal to the rate at which you see the process. So this we have modeled it as a binomial process. You model it as binomial and then you take the limit of n goes to infinity. And then you find the probability that, so this is just really becomes, so you want to find the probability that x equal to k. Limit n tends to infinity. This part is an approximation. You get to the original counting process if you take the limit n tends to infinity. So you need to take the limit of n tends to infinity. So we're trying to find the distribution of the random variable, the number of cars that pass through the point. So you have nck lambda by n whole power k into 1 minus lambda by n whole power n minus k. So this is the success probability. This is the failure probability. So nck, I am writing this as limit n tends to infinity 1 factorial by n minus k factorial into k factorial. This is lambda by n power k plus 1 by lambda by n whole power n minus k. No, so what I'll do is I'll write this as n and 1 minus lambda by n whole power minus k. So now I can write this as the n factorial is just 1 into 2 into 3 so on till n by I have 1 into 2 into so on till n minus k and k factorial. Lambda by n whole power k into 1 minus lambda by n whole power n into 1 minus lambda by n whole power minus k. So I can cancel out the till n minus k till n minus k. Then I have limit n tends to infinity n into n minus 1 into so on till n minus k plus 1 by I bring this n power k to the denominator of this side and I take this k factorial this side. I get lambda by k factorial, lambda power k by k factorial into 1 minus lambda by n whole power n into 1 minus lambda by n whole power minus k. So now this term has nothing to do with is not a function of n. So I can bring it out of the limit. It's lambda power k by k factorial limit n tends to infinity n into n minus 1 so on to n minus k plus 1 by n into 1 minus lambda n power n into 1 minus lambda by n whole power minus k. Now let us examine this term and this term and this term. So here, okay, in power q. So this I can write it as n by n into n minus 1 by n into n minus 2 by n into so on n minus k plus 1 by n power q. Okay. So you can write it like this. You can write this n by n into n minus 1 by n into n minus 2 by n into so on n minus k plus 1 by n. And this you can write it as 1 into 1 minus 1 by n into 1 minus 2 by n into so on till 1 minus k plus 1 by n. So as you keep on increasing n, so the limit of this as limit n tends to infinity would be just uh, 1 into 1 into 1 into 1 into 1. So this is just 1. So the limit of this is 1. And then from the above standard, from this above standard notation of e power k, this the limit of this goes to e power minus lambda. The limit of this goes to 1. So you have three sequences, product of three sequences which have a limit individually. So product of the sequence also will have a limit. Uh, so this basically goes to lambda by k factorial whole power k into e power minus lambda. So basically probability of x equal to k is lambda power k by k factorial into e power minus lambda. And so we get the Poisson distribution. So basically what this says is when you want to model counting processes such that they have independent and identical mm, distributions over any fixed interval of time, and also they have a constant rate. You would like the best way to model this type of processes are using the is using the Poisson distribution. So you want a stochastic process with these properties so that you can better model them. So this is the motivation for why Poisson processes are necessary. Mm. And just to recap, how did I end up at Poisson distribution is I modeled the same process with an approximation of binomial distribution, where I split the time into uh, discrete intervals and I found the probability of one event happening at that event at that interval and same. So if an event happens, then I have a success. If an event does not happen, then I don't have a success. But then there at that in that assumption, you're missing the point that what happens if two of those events happen at at the discrete interval that I've created. So what you do is you discretize the event and then you discretize the index space and then you take the limit to infinity so that you get smaller and smaller mm, increment intervals. And then there you get the Poisson distribution. The Poisson distribution is a discrete distribution, but the Poisson process is a continuous time process because there is no condition on when the event should occur. The event can occur at any real time number. Okay, so now since we have, okay, I'll just come back in 2 minutes. Sorry. Yeah, so now we'll go into Poisson process. So Poisson process is basically a counting process where this term is number of events that has happened. This counts number of events that has happened in an interval 0 to t. So there are multiple ways in which they define a Poisson process. So this is a Poisson process if the following points are satisfied. Arrivals, probability that number of arrivals or number of events that occur between um, E and t plus delta t, a very small delta t, is equal to probability that one arrival occurs between t and t plus delta t is equal to lambda delta t. So this is a constant. This is what we call as the rate, and then order of delta t. So this is a negligible. So what this order of delta t states is as delta t tends to zero, limit delta t tends to zero, then the order of delta t by delta t, this term goes to zero. This is what it means. So this is so small that as you decrease the uh, delta t, the width of the delta t, the this term is so negligible that it goes to zero. So the second thing, probability that more than one arrival has occurred between t and t plus delta t. So this is of the order is delta t. And four, number of arrivals in non-overlapping intervals are statistically independent. So what does this mean is, suppose you have an interval here, you observe this interval and you say that, okay, some number of cars have arrived in this. And then you have another non-overlapping interval you observe here. They say that, okay, some number of cars have arrived. The number of cars arrived here doesn't play any role on the number of cars that arrives here because they both have no overlap. These both are basically independent to each other. Yeah, if you have overlap, then it will depend, like, because if one car has passed here, then both of them will get one. If no car has passed here, both of them will get zero. So it's important that you understand that for non-overlapping intervals, the arrivals are statistically independent. Yeah. So now I'm going to define. Okay, so this is one way to define a Poisson process. So the other way to define a Poisson process is, so if we have NT greater than zero, this is again a counting process. So if it satisfies the following: n0 equal to 0, and t is integer valued, takes integer values 3. If s is less than t, then ns is less than or equal to nt. 4. For s less than t, nt minus ns equals the number of events that occurred in the interval s comma t. So this is very obvious. The fourth one is very obvious. So if we have um, this is s and this is t, then you will have ns here, and this would be nt. If you subtract these both out, then you get nt minus ns, the number of intervals that have happened in between s and t. So this is another way to define the Poisson process. So this is not a definition, like these are the things that it must satisfy, the counting first must satisfy. The definition now is that uh, the second, so this is the definition two. This was definition one. Definition two is one. N0 equal to 0, 2. Process has independent increment. We have seen what independent increments are. So non-overlapping times are independent. And 3. Number of events in any interval of length t is Poisson distribution. With mean lambda t. So what you're basically saying is probability that n t plus s minus ns equal to n is e power minus lambda t power n by n factorial. Using the independent increment and the third property, we can also say that it's stationary. So you no need to always calculate from s to t plus s. It is equivalent to show that from 0 to s has the same distribution as e power minus lambda t power by n factorial. That is so what I'm saying is um, this you are calculating it for the interval s to t plus s. So basically you're moving a, a distance of t. So from the independent increment and the previous thing, it is sufficient to show that from 0 to t, if you have Poisson distribution with this distribution, then you're done. So what we need to show is the definition 1 and definition 2 are equivalent. So to do that, first we'll derive. So we know that definition 1 is correct. We'll derive the Poisson distribution. So from definition 1, we'll say that definition 2 follows. Okay, so for that, so what we need is now I'm defining P and T is probability of n arrivals. So n events have occurred in time interval of length t. So yeah. So now what I want to find is probability that an event occurred in t plus delta t. So this I can write as probability that n arrivals in t and none in delta t, plus probability that n minus 1 arrivals in t and 1 in delta t, and so on, plus probability that 0 arrivals in t and n in delta t. So what I have here is, this is my time, and I have t, and this is t plus delta t. So I want a total of n arrivals in this interval. The probability of that I get n arrivals. So I can, so this total of n arrivals, this event can be split as I get n arrivals between 0 and t and 0 here. I get n minus 1 between 0 and t, I get 1 here. I get n minus 2 between 0 and t, and I get 2 here. And so on till I get 0 in this and n. So as we know that these both are non overlapping intervals. So they are independent of each other. So the event that n arrivals happen in time t and none in delta t, these both productify because they have because they are independent. Similarly, all these events are independent. Yeah, so let me write the events. So let me write, and I know that probability of n arrivals in t is p and t. So based on that, I get p and t into. So now we are using the definition one. Okay, so from definition one, we know that probability of one arrival occurs between t and delta t is this. Probability of more than one arrival occurs is this. So probability of no arrivals occurs between. So okay, let me calculate here only. So probability of no arrivals between t and delta t is 1 minus sum of I equal to 1 to infinity probability of I arrivals between t and delta t. So this I get as 1 minus. Um, so for one arrival, I know it's lambda delta t plus order of delta t. So it's lambda delta t order of delta t. And the remaining are all order of delta t's because more than one. So even if I have an infinite sum of delta t's, these again would form a function which is of the order of delta t. So this is 1 minus lambda delta t minus order of delta t. So the probability of no errors between t and delta t is 1 minus lambda delta t minus order of delta t. So I write that here 1 minus lambda delta t minus order of delta t plus pn minus 1 t into now one probability of one occurring here is order of delta t. And then I get plus pn minus 2 t into order of t delta t and so on till plus p0 t into order of delta t. Now, since these all are order of delta t's, this will again form, this is just linear combination of all functions which go to which are of the order of delta t. This again will be a function which is an order of delta t. So this is basically p of nt into 1 minus lambda delta t minus 1 delta t plus pn minus 1 t into lambda delta t plus order of delta t plus order of delta t. Now what we do is this is pn t plus delta t. So let me call this as here. And then I write it for n equal to 0. For n equal to 0, I get p0 t plus delta t. So no arrivals occur in the first in 0 to t, and then no arrivals occur in t to t plus delta t. So let me call this b. Rewriting b and a, I get, so first I'll rewrite b. So I get delta t. I bring this term to the right, minus p0 t is equal to minus lambda t minus order of t. So I get p0 t into minus lambda delta t minus order of delta t. I divide it by delta t and I take a limit. So this I get dp0 by dt is equal to minus lambda p0. So what did I do here is divide by delta t, take limit delta t tends to 0. Similarly, we can do it for a, and so first we'll solve. Similarly, we can do the same for equation. Here we get pn t plus delta t equal to, sorry, minus pn t equal to minus pn t lambda delta t minus order of delta t plus pn minus 1 t into lambda delta t plus order of delta t. So now again I divide by delta t and take limit delta t tends to 0. I get dpnt by dt is equal to minus lambda pnt plus lambda pn minus 1. So I call this as C, this as D. So first I will solve this. So solving this is pretty easy. dp0 by dt equal to minus lambda p0 t. I take dp0 t by p0 t equal to minus lambda dt. Integrate it on both sides. I get log p0 t equal to minus lambda t plus c. then we can write C e power minus lambda t equal to P0, where C I need to find. Okay. Now here I have got like infinite number of differential equations that I need to solve to find the probability set each. So probability that in time interval 0 I get 0 arrivals. Probability that in interval of length t I get 1 arrival, 2 arrivals, so on. So I'll do it by induction. So one by one I'll do it. So dp1 of t by dt is I can write as minus lambda p1 t plus lambda c upon minus lambda, because I have this I can write as dp1 t by dt plus lambda p1 t is equal to lambda c e power minus lambda t. So now you have an ODE in p1t. You solve this, you get p1t equal to c e power minus lambda t plus lambda t e power minus lambda t. This can be done by using the Laplace transform. This is the solution to the ODE that we have got here. Okay, now the boundary conditions here are, so Pn 0 equal to 0. So simultaneously multiple events can't occur together. That is an assumption for n greater than or equal to 1. Substituting that, you get P1 0 is equal to C plus 0 0. Therefore C equal to 0. And then P1 t you get it as lambda t e power minus lambda t. Now similarly, you solve this one by one, you get P2t equal to lambda t whole square by 2 e power minus lambda t. Then similarly, so what you get is Pnt equal to lambda t whole power n by n factorial into e power minus lambda t. This is the Poisson distribution, which is what the second definition claims. The second definition claims that in an interval of t, you get it with Poisson distribution. So there is actually one more way to define it using the inter-arrival times of the events that have occurred. So I'll go through this in the next class also, but I'll just give a brief view of what is the basic idea of what I'm trying to do. So I have an event occurring at here and here. So let me call the inter-arrival distance with t. So t is a random variable. So what I want to find is the distribution of t. I want to find the distribution. So to find the distribution of t, I find probability of t greater than or equal to 2. Is equal to probability that no arrivals in interval of length t. Okay, so probably these two and that are confusing. So I'm saying that let this be A and let this be B. So an event has occurred in A and event has occurred in B. The time between those two is capital T. Now what I'm saying, what I want to find the distribution of capital T. What I'm saying is that the interval time is greater than some number T. That T is the distribution, is the inter-arrival time. So no arrival should occur in the interval of length T. This is just P0 T. And this is equal to e power minus lambda. So the distribution of capital T is probability t less than or equal to t. This is 1 minus e power minus lambda t. This is the cumulative distribution of t. Now I differentiate it with respect to e, and I get lambda e power minus lambda e. This is the distribution of exponentials, and this is an exponential distribution. So what you've seen is if you have a Poisson arrival process, the intra-arrival time between two uh, events is the exponential distribution. So I'll just give a recap of what I've taught today. So you have an index set T and a state space T. So general random processes take uh, values in this and they are random in nature. Then you have random point processes where at each instance some event occurs, but the time at which they occurs are random. But what we know about this, so these are known as random point process, of which Poisson distribution is an example. What are the assumptions that we've taken is known constant mean rate, lambda delta t, and now we can basically formulate this into look at an interval, find the distribution of the interval. So look at an interval and uh, count how many numbers. So this is the count, how many numbers of events have occurred. So basically the number of events that have occurred is Poisson distribution. The other way is you see the time between two events. And the time between two events is you see that it's an exponential. So these are the two ways you can define a Poisson process. This is what basically we have covered today. We have seen multiple definitions using the Poisson distribution. And next class, I can talk about interval times and time taken for the nth event to occur. So yeah, next class also will pause the process and we can go next class. I'll stop the recording.